I'm going to try really hard in this class to keep doing outlines of what we've covered and remind you what we're working on and stuff like that, because it's a class where there's just so much stuff, unlike statics where there's really like two things, you know, and you just get practice with them. So first of all, anybody have any homework questions?
I have a question kind of regarding when the first law of thermodynamics, when Q is positive or negative, or when W is positive.
Yeah. Yes. So the first law, sign convention. Think of the power cycle, like how you get power in an engine. Okay. You have a cylinder and a piston. You have a gas here. You raise the temperature of the gas, and the piston moves up. Okay? And this cycle tells you the sign convention. Q is positive when heat is added to the gas. And W is positive when work is done by the gas on the surroundings. So in other words, Q is positive when energy is added to the gas. And W is positive when energy is removed from the gas or lost from the gas. Okay, so that's the first law, sign convention, always. And just get in the habit of thinking of how you get power in an engine, you know? Those tell you the sign convention.
Now applying this to question number 4 in the homework.
Yes, every question that we're going to do advanced, you know, more and more advanced stuff with the first law of thermodynamics, and all the way through from now forever, if you're using the first law, this is the sign convention.
Okay, so like when the gas is compressed to raise its temperature, look at number 4.
Oh, do you have it with you? I don't have it. Yeah, let me just look at it. Oh, a heat pump and a refrigeration. Okay, yes. So in first law number 4, so heat pump and refrigeration cycles work the same way. What happens is, if you think of a piston and a cylinder, this is the gas. the refrigerant in this case. The piston is pushed down, okay, and then later, so work is done on the gas, and then at a later part of the cycle, heat leaves the gas, okay? So heat is positive if energy is being added to the gas. So in this case, Q is negative. And work is positive if it's being done on the surroundings, energy being lost to the gas. In this case, work is being done on the gas. You can remember anytime a gas is compressed, work is being done on it. And so in this case, work is less than 0 also. So again, just compare what's happening in whatever case you have, compare it to what's happening in a power cycle. Okay, and that tells you the sign of heat and work. Any other homework questions? All right, so where are we last time? We talked about the first law, and in my introductory lecture, when I like the first day or second day, when I talked about sort of the overall approaches in this class, I said we're going to think of closed systems and we're going to think of control volumes. So far, everything we're doing is closed systems. And what that means is at instant 1 and instant 2, we're looking at exactly the same molecules. You know, if you named them, you'd have all the same, attendance would be perfect, you know. And the first law for closed systems says that the change in energy is equal to the heat minus the work. Where the energy is equal to the kinetic energy plus the potential energy plus the internal energy. Then we also talked about the work of expansion. And that's equal to the integral of the pressure d volume as you go from volume 1 to volume 2. And if the gas expands, work is positive. And if the gas contracts, work is negative. Then another thing that I mentioned was, so this kind of wording is going to come up in problems from time to time, so remember this. So how do you create physically a constant volume process? By the way, that's called isochoric if you want to sound fancy. That is by letting the process happen in a fixed container. a container that doesn't change size. How do you make a process happen with a constant pressure? That's called isobaric, like barometric pressure. You do that by applying a constant external force to the piston. And then the last one is, how do you make a process happen with a constant temperature? That's called isothermal. You do that by putting the gas in thermal contact with a large reservoir at a fixed temperature. Okay, now let me add two things to this list that are new. The first one is, remember that we talked about extensive and intensive properties, right? So extensive and intensive properties. Some of the common ones that we're going to use, two of the most common ones we're going to use, are, remember that the total internal energy is equal to the mass of your system times the specific internal energy. And also remember that the extensive volume is equal to the mass times the specific volume. Okay? So the reason this is important is look at the first law and this expression for the work of expansion, okay? And look at whether those are the intensive or extensive properties. Everything showing up in that first law for closed systems is an extensive property, okay? So if you're given values as intensive things, you need to convert that by using the mass. Okay, same thing with this integral for the work of expansion. Okay, if you're given the specific volume, you need to multiply by the mass to get the extensive volume. And it turns out that often the information we're given is going to be the intensive version of these things. The reason for that is formulas and tables can give you intensive versions, but they don't know how much total you're dealing with, you know? So get used to, thinking about what am I given in this problem? Don't just see the word volume or see the word internal energy and put it into the equations, Think like, is this intensive or extensive? Do I have to multiply by mass? That kind of thing. Okay. The second new thing that you need to keep in mind is, so if you look at number 3, these are all the things for keeping properties constant, okay? There are also things for keeping certain types of energy transfer from happening. So think of these as ways of having zero energy transfer of various types. Work equals 0. But let's just say the work of expansion. There's a couple of other kinds of work. But the work of expansion is equal to 0 if you have a fixed container. So that's the same as keeping the volume constant. But this is the important one, the one that comes up more often, is how do you have heat transfer be equal to 0? Heat transfer is equal to 0 if you have a well-insulated container. Okay? Sometimes also, later on we'll see cases where if things happen fast enough, no matter how poorly insulated the container is, there's not enough time for much heat transfer. But for now, just think of insulated. So if a problem says something about insulated, remember that Q is 0. Okay? All right, let's do an example. So let's say we have a system. That's a 0.5 kilogram combination of a gas and its container. Um, 100 joules of work is added to this system. And 50 joules of heat is added to the system. And the system goes from a speed of 3 meters per second. Oh no, it goes from a speed of 0 to 3 meters per second. And the height lowers 2 meters. So first, what's the change in the system's internal energy? And second, what's the change in the system's specific internal energy? Okay, well, we're going to use the first law of thermodynamics. So we're going to use the fact that the change in energy is equal to Q minus W. And we can expand, usually, often, our energy is just going to be treated as the internal energy. But now we know that we're dealing with some kinetic energy and potential energy stuff. There's no reason to eliminate those. And so we can expand this change in energy to be the change in kinetic energy plus the change in potential energy plus the change in internal energy. And that's equal to Q minus W. So let's first think about the kinetic and potential energy. Kinetic, we're going from, to get the change, we're going to take the ending kinetic energy minus the starting kinetic energy. So this is going to be 1/2 times the mass of the system times the later speed squared minus 1/2 times 0.5 times the starting speed squared, which is 0. And so this is 2.25 joules. The change in the potential energy, all we have is gravitational potential energy. And so this is going to be mg times the change in height, which is -2 meters. So this is 0.5 times 9.81 times -2, which is -9.81 joules. Okay, now we have to think about the sign convention for the heat and the work. A positive value of Q, does that mean energy added to the system or removed from the system? Added to the system. So 50 joules of heat is added to the system, so Q is going to be equal to positive 50. And then what about work? That's going to be negative, that's right, because a positive value of W is energy being removed from the system. Okay, this is added to the system. So W is equal to -100. And now let's put this all into the equation. This is sort of our expanded equation. So we have 2.25 minus 9.81 plus delta U is equal to 50 minus -100. And so this says -7.56, right? Plus delta U is equal to 150. And so delta U is equal to 157.56. And this is joules. Then if we want the specific internal energy, delta U is equal to the mass times the change in the specific internal energy. So the change in specific internal energy is just 157.56 divided by 0.5. And so that is 315.12 joules. Joules per kilogram. Okay? Yeah. Okay, let's do one more example before we go on to anything new. So let's say we have 1 kilogram of gas, and it goes from a specific volume of V1 of 0.5 cubic meters per kilogram to a specific volume V2 of 0.3 cubic meters per kilogram. The setup is going to be a freely moving piston with a mass of 5 kilograms. The gas is here. And the cross-sectional area, the circular area of that piston is 0.02 meters squared. So first, we want to calculate what's the pressure for the gas. And second, we want to calculate if the cylinder is insulated. What's the change in specific internal energy of the gas? Let me give you one other bit of information. Let's just simplify this a little bit. Let's use the fact that the atmospheric pressure, we're just going to call it 1 times 10 to the 5th pascals. Okay, so remember I said that in order to have constant pressure during a process, you have to apply a constant external force to the piston. Well, this is a case where a constant external force is applied to that piston because there are two parts of that force. There's the atmospheric pressure pushing down, and that's not going to change. And then there's the weight, and that's not going to change. Okay? So if this thing is going to stay in equilibrium at these two states, we can calculate what the pressure is in the gas to maintain equilibrium. Okay, so I'm going to start by drawing a free body diagram, like from the side of the piston. So that's a side view of the piston. And the forces we have acting are a weight force pushing down. So 5 times 9.81 is the weight. Then we have the force pushing down that's caused by the atmospheric pressure. So that is the cross-sectional area, 0.02, times atmospheric pressure, which is 1 times 10 to the 5th. And then pushing up, we have the pressure of the gas. So this is going to be P times the cross-sectional area. All right? We're going to balance those. I'm going to call up positive and down negative. So we have negative 2 times 10 to the 3 is the 0.02 times the atmospheric pressure. Minus 49.05 plus 0.02 P is equal to 0. And I use different numbers. Can someone calculate that for me? So this is, so we got 0.02 P is equal to 2049.05. So 50 times that, I could almost do that. $102,000 what?
452.5.
452.5 pascals. Okay. So that has to be the pressure in the gas. Now we're going to use the first law. So this was part A. For part B, we're going to use that the change in energy is equal to Q minus W. This is insulated, so we know that there's no heat transfer. And since this is a gas and we're not given anything about kinetic energy or potential energy, we can't calculate those. We're going to treat the change in energy as just the change in internal energy. So we're going to forget about those. Okay, so what we're left with is the change in internal energy is equal to negative W. We're trying to come up with the specific internal energy, which we could get since we know that it's 1 kilogram of gas. We could calculate that as soon as we can calculate the change in extensive internal energy. So if we can calculate that work, we can get it. Is there a way that we can calculate that work?
Yeah, the integral.
Yeah, that's right. Remember that the way this is set up, we have a constant pressure, okay? So the work is equal to the integral from volume 1 to volume 2 of PdV, and this pressure is constant. And we just calculated what that is. We need volume 1 and volume 2. We're almost given that, but not quite. This is one of those cases where you have to be careful. We have 1 kilogram of gas. So V1 is equal to 1 kilogram times 0.5. I should have chosen a different volume so it changed the numbers. Okay, so 0.5 meters cubed per kilogram. Nope, now we got rid of the kilogram, so this is just meters cubed. V2 is 1 kilogram times 0.3 meters cubed per kilogram, so that gives us 0.3 meters cubed. And so W is equal to 102, so I'm pulling the pressure out of the integral, 452.5 times the integral from 0.5 to 0.3 dV. And so that is 102, 452.5 times negative 0.2. Can someone tell me what that is? Ooh, it's going to be this thing, right? 2.
Yeah, negative 20,004.
Negative 20,000 for 40. Negative 20,000 for 90.5. Is that it?
Yep.
Okay. Okay, so that's W. Now we can go to this equation, and we get that the change in internal energy is equal to negative of negative 20,490.5. And so the change in internal energy is positive 20,490.5. Everything's in SI units, so this is joules. Then finally, we want specific internal energy change. So this is delta U divided by M. M was 1 kilogram, so this is 20,490.5 joules per kilogram. Any questions about that? I would describe this like there's not a lot of conceptually hard stuff here, but it just takes doing a bunch of problems before you start to see your way from equation to equation. What do I know? What can I get? How can I bounce from here to here, you know? All right, the next thing that we're going to do is this is the equation that we've been using for the first law is for a finite time interval. We can also write this in a differential form. So sometimes it's useful to use the differential form of the first law. And we'll write this as the time derivative of the energy is equal to Q dot minus W dot. Normally in dynamics, Q dot is totally synonymous, or anything dot is totally synonymous with the time derivative of something. In this case, we're using the different notations to mean something a little bit different. So let me tell you what these mean. So dE dt is exactly what you would expect it to mean. That's the time rate of change of energy. But Q dot is the rate at which heat brings energy into the system. And W dot is the rate at which the system does work on the surroundings. And when we're using the differential form of the first law, we're going to break problems into two different types. So two different types of problems. The first one is steady state. And steady state means that over time, the energy of the system doesn't change. So dE dt is 0. And then the second type is transient, where this isn't 0. So dE dt is non-zero. The first case where we want to use this differential form, so this differential form of the first law it's useful for heat transfer problems. And the next thing we're going to do is go into some equations for transferring heat. So for heat transfer calculations, there are three types. The first one is heat transfer through conduction. Conduction is energy being translated from point to point through a material without the material itself moving. Like if you heat up the bottom of a pan, eventually the handle gets hot. Okay, that's conduction. The second one is radiation. Radiation is how we get energy from the sun. It's like if you stand in front of a fire, it's why your pants get hot. And the third one is convection. And an example of convection is wind chill. Any of you guys ever had to take an ice bath for like sports or something, for an injury? So you put your foot in like a bucket of ice water, you know, and at first it's like so painful because it's so cold. But then you start to think like, oh, I'm getting used to it. And then the trainer or whatever comes and stirs it. And you're like, oh my God, it's as bad as it was before. So that's convection. If you put your foot in ice water and just let it sit there, your foot's going to heat up the water around your foot, you know. And so the water is going to get warmer. And if you stir the water, water molecules that are warmer will go away. Water molecules that are colder will come towards you. And that motion of molecules is going to carry energy. Okay, so in the next class on Friday, we're just going to get into calculations of these and putting those into the differential form.